Yes, welcome to the last session of our statistics class, which will be on introduction to inferential statistics. We really appreciate Dr. Lani for finding time to be here to continue the teaching that I started last week. Thank you very much, sir. You have the floor.
Thank you, Dr. Kudos. Thank you, Prof, and thank you everyone for having me. I really count it a huge privilege to share some insights with us all. So, like Dr. Lawal said, we are continuing from where we stopped the last time, talking about quantitative analysis. The last time we looked at descriptive analysis, and this morning we'll look at the other counterpart, which is the inferential statistics. I always like starting with this slide of the research process. It's just like a foundation I love talking about. You know, whenever we are doing research, we start from the research title, the research question, and it goes through the literature review, hypothesis. Then we talk about the different types of approach, the designs of your study, the sample size calculation, how you now select your sample, variables and measurement scale. That's for designing your questionnaire. You now collect your data, you have your data analysis, you report your findings, you realize that there are some things missing, and then you start another study. You know, so it's a continuous circle. But we are still here talking about data analysis. So hypothesis testing is a formal process of statistical analysis using inferential statistics. What I'm trying to say here is, the last time we spoke, we were talking on descriptive statistics. When you have a research question, it can either be descriptive or inferential. When it's a descriptive research question, all you need to do is descriptive statistics. But the moment you have an inferential research question, that is where you need inferential statistics. And the goal of hypothesis testing is to compare population or assess relationship between variables using samples. Please look at this analogy. You have a population, but what you have is the sample. So you are trying to use the sample to make inferences on the populations. There are some things we consider, you know, in selecting the appropriate test for our hypothesis. And when you don't select the appropriate test, it affects your significance and even the relevance of the study. I'm talking about the study conclusion itself. So these are some things we need to put in mind when we want to select the particular type of analysis for our data. You need to understand your study design, and I'm going to explain them as we continue. You need to look at the number of groups to compare. You might be doing a study in just a group, that is group A. So if it's just one group, the kind of analysis might differ depending on the research question. But you might be comparing group A with group B, you know, which you normally see in experiments, or you can even have group A, group B, group C, and etc. You know, so depending on the number of groups you are working on, your statistical test will also differ. The research question that you crafted will also determine the kind of inferential analysis you do, your hypothesis, and the type of data you collect, and the measurement scale of your data. Maybe I should just ask that even the kind of variable that you have is also a determinant on the kind of analysis. But nonetheless, the variable actually determines the kind of data anyway. So it's like it's interwoven. So number one, study design. The design in a large extent is actually more important than the analysis. The reason being that if you have a badly designed study, it's like the foundation is already faulty. Whatever you build on it is a waste. You know, a badly designed study cannot be retrieved. But when you have an analysis that is poorly done, it can be reanalyzed. Carry your data, go to another statistician, and you reanalyze and you have a good data. So a study design is very, very important. And the simplest way to categorize study design is with reference to either the presence of an intervention or the absence of an intervention. So when we say we have study design, and then there's absence of intervention, we call that kind of study observational. And if there's the presence of an intervention, we call that one experiment. You know, and this one is further divided into so many other branches, likewise for the experiment, but that is not the focus of today's class. So like I was saying, the type of study will determine the kind of inferential analysis that you're going to do. The number of groups, like I was saying some 2 slides before, if it's just one group, you might want to look at the pattern, the prevalence, the distribution of particular variable in just one group. But when you're having more than one group, that's 2 or more, you might want to compare between group A and group B, group A, B, and C, A, B, C, D, and as much as possible. And that will also determine the kind of analysis that is going to be used. The groups can either be equal or different. You might have equal number in group A, equal number in group B, or they might differ in the numbers of the participants. So when you are comparing 2 groups, you can use a t-test. We call that the independent sample t-test, the student t-test. You can use the chi-square, McNemer test, Fisher's exact test, Mann-Whitney U-test, Spearman correlation, Pearson's correlation. All these are in situations where you have or you are comparing or checking relationship between 2 groups. When it is more than 2 groups, we are talking of 3 or more. That is where an analysis like ANOVA comes into place. Kruskal-Wallis, log rank test, Friedman test, multiple linear regression, chi-square test. So chi-square test can be used for 2 groups. It can be used for more than 2 groups. And interestingly, it can also be used for 1 group. And let me also go back and tell us that t-test can also be used for 1 group, but it can't go beyond 2 groups. We call it one sample. This one is one sample t-test. But 2 groups, there are 2 types. It can either be paired sample, and I'm going to explain that as we continue, or independent sample t-test. All right. So
And Professor
Hello,
Taiwo,
sir.
we lost your voice. We
I
lost
think
your
he has.
voice.
Okay.
He's here, but and he's not muted, but we can't hear him. So we just wait. Yeah.
Okay. So you can pause the recording, man.
in the kind of analysis you do, normally our research questions are phrased with some of these terms. You want to know the difference between A and B, the probability of A on B, the effect, the odds, the impact. So the research question is that is actually what I use basically in choosing the kind of analysis I'm going to work on. Then we'll talk about the hypothesis also. The hypothesis is just the research question crafted, in a conditional statement, So when we want to select a test, another important thing is what is the main study hypothesis? So invariably, we are still talking about the research question. In some cases, there is no hypothesis. Like I said earlier on, if you have a descriptive question as a research question, you just want to see what is there, the prevalence, the pattern, For example, in prevalence study, you don't have hypothesis. And if there is no hypothesis, then there is no statistical test. But that does not mean that you don't have descriptive statistics. It's just that you don't have a test of hypothesis, but you end up with a descriptive statistics. On the other hand, if your question is inferential, then you can perform a statistical test. The type of data collected, and I remember in the last class, I also emphasized on this, that we have quantitative and qualitative data. And then we'll talk about the measurement scale. The quantitative is the continuous or discrete data. The qualitative, or what we call the categorical data, can be nominal or ordinal data. So the type of data, determines or indicates the kind of analysis. For example, there are analyses that are done for ordinal data, and there are those that are basically done for nominal data. And as we continue, you will see such inferential analysis. The measurement scale is just a follow-up of the kind of variable. We have 4 types of measurement scale. The nominal scale is for nominal data. The ordinal scale is for ordinal data. These 2 are qualitative or categorical data. The interval scale and ratio scale are used for quantitative data. So the measurement scale also determines the kind of analysis that can be used. And for the measurement scale, the least among the four is the nominal data, then followed by the ordinal, interval, and ratio scale data. I wouldn't want to go beyond this because measurement scale on its own is a separate lecture. But I just want to work with the assumption that we have an idea what I'm talking about. The number of variables is also very important. We have univariate studies, that's just one group or one variable, and that is the one that we normally use descriptive statistics to express our findings. Bivariate and multivariate, that one is talking about two or more groups. That is where we have our inferential statistics. Inferential statistics. Obviously, when we are talking about bivariate, you are trying to compare one variable with another variable to check the relationship of one variable with the other variable, and on like that. That is why it's bivariate. And there are situations where the variables in your research questions are more than one. There are many multivariates, and that one we can now have inferential statistics also to answer that. So before I go further, because I'll be talking about some variables in the course of this class, just want to revise with us briefly what a variable is. A variable is the characteristics that can assume values. Age, time, distance, anything that can vary is a variable. And you can then assign a measure to it. Variable is a characteristic that changes, unlike a constant which does not change. And variable can be quantitative or qualitative. And it's actually the variables you get from quantitative sources that are quantitative data. The ones you get from qualitative variables are the qualitative data. So if you look at the variables, it actually follows the definition and the types of data. So variables are what generates, excuse me, variables are what generates data. So that's just about variables. Now, there are other types of variables that I want us to have in mind as we continue. When we say a variable is binary, that means that it has only two levels of expression, like a yes or no, dead or alive, present or absent, here or there. It's binary, it only has two levels of expression. I was going to say male or female, but with the kind of world we are now, it's no longer binary. It is actually nominal. There are so many classifications of gender now, so that cannot be a binary variable. But I want us to know that a variable that has only two levels of expression, dead or alive. You are either dead or you are alive. They can't be in between. Those ones are called binary variables or dichotomous variables. When we say dependent variable, normally in inferential statistics, we have a relationship of X having a relationship with Y. So if this relationship was an experiment, or we are trying to look at the effect of X on Y, if it was an experiment, we call Y the dependent variable, while X is the independent variable. For example, what is the effect of fasting on body weight? So body weight will be our Y. Y fasting will be our X, because we are looking at the effect of X on Y. That is why we say the presumed effect in an experimental study. The independent variable is the cause. Another name for that is the manipulated variable, the treatment variable. And in this situation here, the X here is the independent. If our research is not an experiment, and you are trying to look at possibly relationship between the number of hours you spend reading, and possibly exam scores, let's assume that is not an experiment. In this situation now, our exam scores, which is the Y, is going to be referred to as the outcome variable. While the number of hours spent reading is going to be the predictor variable. So I want you to have that in mind, because when we go to analysis, it's something that comes up, especially when you are working with SPSS, it will be asking you for the dependent variable. So if you don't know which is which, you end up making a mistake. So I want us to just have this at the back of our mind, that we have binary variables, We have dependent variables or outcome variable, depending on which one you are doing. We have independent variable, the predictor variable. That's independent variable or predictor variable or treatment variable or manipulated variable. It's the one that you usually manipulate to look at the effect on the outcome or dependent variable. So this is the analysis strategy. I shared this slide with us during the last class. This is where we spoke about descriptive variable. Descriptive analysis rather, where we are working with one variable, and then we went through most of these examples when you have a continuous variable, when you have a categorical variable. The continuous variable is the quantitative variable, the categorical variable is the qualitative variable. And I remember we spoke about mean, median, and mode. We spoke about variance, standard deviation, range, percentile, interquartile range, and then we spoke about the normal distribution. I'm sure we didn't discuss about this. And then we went to plots. We spoke about histogram, box plot, stem plot, dot plot, line plot, and time series. And for the tables, this is table frequency. We have the count, the frequency percentages. We didn't talk about odds here. And then for the plot, again, that's for the categorical variable. We spoke about bar chart, pie chart, and Pareto graph. This was our last class. Now, in descriptive statistics, you use it to report on samples and population. And the purpose is just to describe the data that you have, just to describe, emphasis on describe. There's nothing more than that. You summarize and organize information, and it helps to bring about comprehension of the characteristics of a population or sample. And I said earlier on that the number of variable matters in our choice of statistical test. If it is one variable, descriptive statistics, more than one variable, two or more, then we have inferential statistics. So let's go to inferential statistics, starting with when we have two variables, that's bivariate. The inferential statistics allow us as researchers to make decisions or inferences by interpreting our data patterns, which is usually taken from samples. And you can classify inferential statistics to be either parametric or non-parametric. What does that mean? The difference between parametric and non-parametric is that the parametric test relies on some assumptions, based on the source of the data, whereas non-parametric does not depend on any assumption or any distribution. As we continue, I will explain more what that means. So what it means literally is that a parametric statistics makes assumption about the parameters. Remember, I spoke about parameter and statistics in the last class. Parameters are those characteristics from the population. Statistics are the characteristics from the sample. So in parametric inferential analysis, it makes an assumption from the source, from where your sample was extracted, and that assumption is that the population follows a normal distribution. That is what it means. In the non-parametric, there's no assumption like that. That means that the population, to a large extent, is not normally distributed. That is the population from where you sourced your sample. So non-parametric statistics are more commonly used for variables at the nominal. And you can see it's coming up now, nominal or ordinal level of measurement. When we say nominal, it is qualitative. Remember, qualitative is categorical data. So it is normally used for things that you classify, things that you order, not for quantitative variables. That means that they do not have a normal distribution. Normally, it is things that are measured, like age, distance, weight, height. Anything that is measured is normally taken to have a normal distribution. However, non-parametric tests are things that are classified, or categorized or ordered. They are not normally distributed. So analysis for such kind of data will be non-parametric. So this is what I'm saying. For the population, you take a sample. The sample is what you are working on. The population characteristics is what we call the parameter. And that of the sample is what we call the statistics. So if you are collecting, let's assume these are your sample, and what you are collecting is possibly the weight of all the sample. And you want to do an analysis, possibly the weight and height. Those are the things you are collecting as your data. Now, we have to look at the parameter and make an assumption that, okay, wait, from the population, normally in every population, every measurement is normally distributed. Same with height is a measurement. But let's assume you are looking at gender in your population, gender, and then maybe you are looking at maybe occupation. These two are not normally distributed. So the kind of analysis you will use for these two differs from the one you will use for these two. That's all I'm trying to say. So these two, because they are not normally distributed, you will use a non-parametric analysis, while this one you will use a parametric analysis, and I will explain as we continue. So back to the bivariate analysis. We have another table here, and I want you to recall what I said about the type of variables. Remember that normally we have X relating on Y. Our Y is the dependent variable. Our X is the independent variable. You can see it here, dependent variable or outcome variable or response variable. Our X is independent or explanatory or manipulated or treatment variable. They have many synonyms, but you can just hold on with independent and dependent. I think that's easier. So when we have two variables, and these variables are going to be in your research question, so you must be able to identify the kind of variables you are talking about from a sample research question. That's why I said the research question is actually the best way of identifying the kind of inferential analysis we use. So let's assume your X and your Y are both categorical. That means they are qualitative. Like in the previous slide where I was talking about gender and occupation. So if I was to look for the relationship between gender and occupation, gender is categorical, occupation is also categorical, then I'll be looking at something like a chi-square, features exact, McNeman test, and look at the condition here when I have only two categories. But I can't use what's it called? I can't use this particular analysis because in my occupation, most likely I will have more than two categories as my dependent variable. I can have civil servant, artisan, professional, all manners. So this particular one will not work. It will only work if my independent variable is binary and my dependent variable is also binary. So let's assume for this class, that gender is just male and female. And let's assume that maybe you are either successful or not successful as our category. That's for the dependent variable. And our research question is saying, what's the relationship between gender and success in life? Where success in life is either success or not successful. In this particular situation, because my X is 2, has a maximum of, is binary, okay? My Y is also binary. That is when this particular one will work. In situation where my X and my Y, there are more than two categories, like I was saying earlier on about sex and occupation, that's where this will come into play. You can see the condition here. X or Y is more than two categories. And that is because both of them are categorical. So we can use chi-square for categorical variables. We can use Fisher's exact, McNeman's test, Hansel test. There are some small indications for the choice of which one you eventually use. But this is just like an overview. It is when we are talking about chi-square that we can now go deep and explain the particular kind of analysis that is one will use for such. Now, in a situation where our dependent variable is continuous, now I think you understand what we are talking about, and our independent variable is categorical. That is where you have to now check if your dependent variable, if there's an assumption of normality, if it is normal, that is where you use what we call a parametric test. By the way, all of these are non-parametric so that you can understand because they are all categorical. You will check if your Y is parametric, it follows a normal distribution, and you check if your Y is non-normal. Sorry, this is the one I'm looking for, non-normal or non-normal. So the one that has Y as normal and over two tests, t-tests, both paired and two sample tests, those ones are parametric tests. When your Y is non-normal and you still want to do an analysis on a continuous variable. So by the way, a variable can be continuous and not normal. and we can check for normality to know which one is ideal. So if it is not normal and it's still a two group, you can use Wilcoxon rank sum, Wilcoxon sign rank sum. ANOVA is for a variable that the dependent variable is normal, but it is more than two. So you use t-test when you have two groups. You use ANOVA when you have more than two groups. And I'm going to show us an example. This might be a bit complex, but when I start talking about class examples, you will see what I'm talking about. The non-parametric variant of ANOVA is the Kruskal-Wallis test. By the way, let me just remove this. The non-parametric variant of the independent sample t-test is the Wilcoxon rank sum test, while the non-parametric variant of the paired sample t-test is the Wilcoxon sign rank test. They all have the variant in case your dependent variable does not follow a normal distribution curve. Now, if you have a situation where both your independent variable and your dependent variable are both continuous and they are both normal. For example, I might want to check what is the correlation between weight and height. Just to check the correlation between weight and height. Both of them are supposedly normal variables. In that situation, we do a scatter plot, or a correlation. We can do a linear regression. Yeah, that's the correlation. That's a scatter plot or a correlation, and we are going to have an example in the class. But let's assume that both of them are non-normal. That is, both X and Y are not normal. For example, maybe I'm looking at educational level. Remember, educational level is ordinal because it's going up or down. I'm looking at educational level and maybe cancer stage. Cancer stage, you have stage 1 to stage 4. It's also ordinal. This kind of, what's it called? This kind of question, actually, I cannot use this because this is going to be categorical. But there are situations where we can use, we can have X and Y as ordinal, like position. Thank you. That idea just came. Position in class. Normally, somebody will be first, second, third, fourth, and so on. Position in class, it's a kind of variable that is not normal, but it's ordinal because it is hierarchy. Position in class, and maybe salary. Position in class and salary. Salary too is going to be ordinal because there will be high salary and low salary, and there's going to be a kind of cadre, So if you want to check a relationship between two ordinal variables like that are in numbers, they are both continuous, but they are ordinal, that is where you come and use what we call a Spearman's correlation. Another name for this correlation is rank correlation. So it even gives it out that you need to do something that is based on rank. That is for a bivariate analysis. Let me just quickly go over it once again. So we have a situation where both your independent and dependent are categorical. Then you have some choice analysis to work with. You have a situation where one of them is continuous, that's the dependent variable, and the independent variable is categorical. Then you have options to check if your dependent variable is normally distributed, then you work with parametric test. If it is not normally distributed, you work with the non-parametric variant. And then there are situations where both independent and dependent are normally distributed. You have scatter plot regression, and then you have your Pearson correlation. And situations where both of them are non-normal, you have Spearman's rank correlation. Okay? And when we have more than two variables, what we've just discussed here has to do with two variables. Now, there are situations where you are checking the effect of 2, 3, 4 variables on one dependent variable. In situations where you have more than two variables, and that's your research question will have brought it up. And then you also want to look at how to analyze. That's where we have the multivariate variables greater than two variables. And these are the examples that you can have. Remember, our Y is a dependent variable. So look at this example of multiple linear regression. So for us to do a linear regression, one of the assumptions is that your Y, that's the dependent variable, is normally distributed. That is why regression is a parametric test. And I want to, let's assume I'm looking at weight. I might want to look at the effect of age, maybe hours of sleep, and maybe quantity of food taken. I want to look at the effect of these three independent variables on weight. That is where I will have to use a multiple regression. If it was a linear regression, I will be talking about only one variable, maybe age and weight. But multiples denote or connote that you have more than one independent variable. You can also use that for analysis. You can use analysis of variance, when you have multiple variables, and analysis of covariance. Those ones are not for us at this level. We have logistic regression, very interesting, and that is used for when your dependent variable is dichotomous. And I remember talking about dichotomous as binary variable. So your outcome variable has only two shades of expression, either yes or no, true or false, male or female, here or there, dead or alive. It's just dichotomous. And I have some example to show us. Sometimes your dependent variable can be greater than two categories. There you use multinomial logistic regression. Your dependent variable can be an ordinal variable. You use ordinal logistic regression. And then there is survival analysis. And then we have multivariate, dependent variable. So these are a bit on the advanced level. We'll just look at some examples, from these three in the class work. So going back, we have bivariate analysis, and there are sample inferential statistics that can be used. And then we have the multivariate, and they are basically regression and logistic regression, basically. And then we have factor analysis, life table analysis, proportional hazards, and cost hazards. So that is for that. Now, this is a simple class example for us to see what I'm talking about. This is for correlation. You are trying to check whether two variables are related. The test here is Pearson correlation. The predictor variable, which is our x, the outcome variable, which is our y. So our x is continuous. By now, you know what that is. Our y is also continuous. And I have an example here. What is the relationship between height and weight? Because both height and weight are continuous variable. That's why I said, if you have a good research question, from the research question, you can tell the particular analysis that will be used. That is where statisticians collect our money, because they understand this. Once they see the research question, right from the proposal, they know the analysis they are going to do, and then they charge us. If you know this, you can also do your analysis yourself. In a chi-square test, you are still trying to check whether two variables are related. Because our x is categorical and our y is categorical, you use a chi-square test. Look at the question, the sample question here. What is the relationship between educational level and socioeconomic status? So here we have either no education, primary, secondary, tertiary. Status can be maybe poor, maybe average, and maybe very rich. It depends on how you classify it. However, both of them are categorical. In a situation like that, what you can use is a chi-square. Okay, look at this example here. When you are trying to compare among means, I said something about paired t-test. As an example of t-test, there's an independent sample t-test. There's a one sample t-test. Look at the example here. We have our predictor variable is still our x, and our outcome variable is still our y. The predictor is categorical, the outcome is quantitative. Let me explain what I mean here. Look at the sample question. What is the difference in the average knowledge of the choice of data analysis before and after this lecture in this group? So assuming I'm going to give a pre-test and a post-test before this study, and I want to see the effect of my class, if it has improved your knowledge of data analysis, and then I have a pre-test, a post-test, and I'm checking the average to see which one was better. I'll be using a t-test. Now, our categorical variable here is this group before and after. That is the category I'm working with here. I'm looking at you as a group before, I'm looking at you as a group after. That's the categorical. And the knowledge of the data analysis is my outcome variable, because the knowledge I'm going to score it either in percentages or whatever. That's my outcome variable. So when you have a test that has to work on one group and then you are trying to check before and after. So this is what is normally used a lot in experiments, because in experiment, normally you have a baseline, you do your intervention, you have the outcome, and then you compare. So we normally use a PRT test, especially if you are working on one group. But there are occasions where you have one group, group A, and another group, group B. And that is where we have the independent sample t-test, where we have a categorical group, that is group A and group B, and we are still checking for a particular outcome. So look at the sample question. What is the difference in the knowledge of the choice of data analysis after this lecture in group A and group B? So I might have a group A that did not have this lecture, and I assess them on data analysis, the choice of data analysis. And then you as group B that had this lecture, I will give you the same question. So I'm giving them the same question and you are getting the same question. However, in this group B, there was an intervention, and I want to see if my lecture had made any difference. That's an independent sample t-test, because there are two different groups. The two groups can have the same number of participants, but as long as they are different, that is where independent comes in. I hope I'm making some sense. Now, in analysis of variance, which is ANOVA, it's similar to these two that we have done. The only difference is that you are checking in more than two groups. That's the only difference in analysis of variance. So I have an example here that what is the difference in the average pain level. So I have a pain level measurement, maybe from 0 to 10. 0 is least pain, 10 is severe pain, and people are picking the level of pain that they have. When I use 3 types of anesthesia for my tooth remover, so maybe we have anesthesia A, that's group A, anesthesia B, that's group B, anesthesia C, that's group C. Maybe I have like 20 here, maybe 30 here, maybe 14 here, whatever, any number. And then I have measurement of pain from all these participants using 3 different types of anesthesia. So for this group now, I have 20 records for here, I have 30 records, 14 records here. And I want to see which one is the best anesthesia, comparing the 3 together. And because it is 3, that is where ANOVA comes in. If it is only 2, let's assume it is A and B, because there are 2 different groups, I will be using independent sample t-test. So it's just some little tweak here and there. That's how it works. We are going to do a class example. I have an hypothetical SPSS data. So linear regression, you want to look at cause and effect between 2 variables. And like I said earlier on, in linear regression, both the X and the Y are continuous. So this is X, this is Y. Look at the sample question here. What is the effect of the number of hours? That's quantitative. Exam scores, that's quantitative. So I want to check if there's any effect on the number of hours I spend reading if I'm going to have an improvement in my scores. You know, that's a regression. And multiple linear, all that means is that you have more variables in your X column. Your dependent variable is still 1. Look at the sample question. What is the effect of the number of hours of study 1, age of the students 2, the type of school attended 3 on exam score? So that is multiple linear. As long as it is, you have about 2x, it makes it multiple. But in simple linear, it's just 1x. And I want to bring your attention to something. You will notice that in this multiple linear, type of school attended is categorical. It doesn't affect it. You know, as long as it's more than one, any kind of variable can come in, and there's a way you interpret that. In logistic regression, I emphasize earlier on that you only use it when your Y is binary or dichotomous. And you can have simple logistic regression or multiple. It is simple if you have only 1x. It is multiple if you have more than 1x. And look at the sample question here. It says, what is the effect of the hours of sleep on the survival of a patient in ICU? So this is my X, this is my Y. Survival of a patient is either alive or dead. You can't have anything beyond that. So, and that is dichotomous or binary. It is a logistic regression that will be able to answer that kind of a question. This is another example here. Correlation, I said we have 2 continuous variables. Pearson's correlation. is blood pressure and weight correlated. Blood pressure is continuous, weight is continuous. T-test or ANOVA, you are checking the means from a continuous variable taken from 2 or more groups. You use a t-test, you know. Do normal weight group 1 have that's the normal weight, that's group 1. You are checking the weight in group 1 and that of group 2 to see if there is a change in blood pressure. So because this one is group 1 and group 2, you are going to be using independent sample t-test. Like I said, you use only a paired sample in a one group before and after. That is paired sample. Now, if you are checking the normal weight in group 1, group 2, and maybe group 3, at that level, you cannot use a t-test again. You will now have to use ANOVA. Please don't forget that. The only difference between t-test and ANOVA is that ANOVA is used for more than 2 groups for a quantitative analysis to check for means. But t-test is 2 groups or less. Chi-square, I said earlier on, that is for categorical variables. You know, and look at the example here. Are obese individuals, that is obese versus not obese, significantly more likely to have a stroke, that is stroke versus no stroke. So this is one category. You are either obese or not. This is another category. It's either there's stroke or no stroke. That's a chi-square. Logistic regression, as in the last slide, it is where your y is a dichotomous variable. Your y is dichotomous or binary. Does obesity predict stroke? So your stroke is either yes or no. And then obesity, you can either weigh, you can have measurement or whatever it is. That's logistic regression. Always remember, when your y is binary, you use logistic regression to check or to do your inferential analysis. So this is our examples of non-parametric tests. These ones are, okay, this one is non-parametric because the variables here are categorical. This is parametric, this is parametric, this is parametric. Let me go further backwards. All these are parametric because they are all regression. Let me see, all t-tests and ANOVA, they are all parametric. They are all parametric, okay? So for examples of non-parametric, I said earlier on that we have a correlation that you use ordinal and ordinal variables. We call it Spearman rank correlation. That's an example. So when your variables or your research question is comparing 2 ordinal variables, you cannot use a Pearson correlation. You have to use a Spearman correlation. That is the only way we know that you know what you are doing. A sign test is when you are talking about a t-test. It's the variant of a t-test if your variable in the t-test is not normal. You use a sign test. And I said Kuskawali is the variant of an ANOVA where your variable is not normal. ANOSIM is analysis of similarity, unlike what we have in ANOVA, analysis of similarity. Wilcoxon rank sum test is similar to the independent sample t-test, but it's only when your variable is not normally distributed. While the Wilcoxon signed rank test is for a paired t-test when your variable is not normally distributed. So why all this noise? That means that if you are going to do an analysis, it is advised that you do a normality test for your variables. As simple as that. And normality test can be you plotting your histogram, and there are some analysis to check for skewness, to check for kurtosis, to check for, yeah, I think we mentioned it, to check for the standard deviation. So there is a way you can quickly check for normality. You can also use what we call a PP plot to check for normality. You can use a QQ plot to also check for normality. So that is the first thing that a statistician should do. And after checking for normality from your data, they can now suggest that, okay, we are going to use a parametric test or a non-parametric test for the analysis. Now, there are some data that by default, they are not normal, like categorical data, nominal and ordinal. You don't need to check for normality. There's nothing you are checking there. By default, they are not normally distributed. So those ones just go straight for your non-parametric test. So we are going to do some class examples now. I have like a mock data set. Age. And from our understanding of data, age is continuous. I have gender or sex, and for the purpose of this class, I'm limiting it to binary, that is male or female, for the purpose of this class, so that we can have some binary variables. I have BMI, which is continuous. I have lipid level, that's the blood lipid level, which is continuous. I'm going to show us. I have stroke, that is binary. It's either the person has stroke or he doesn't have stroke. Hypertension is also binary. It's either there's hypertension or no hypertension. For the basis of this class, it can be borderline if you want to extend it. But for the basis of this class, we are stopping there. Educational level is ordinal. That means it's either 0, no education, primary, secondary, or tertiary. Income per day in Naira, that one is figures. That's also continuous. So I'm just quickly going to share what's called. I'm going to share, I'll stop sharing this, and then I will share the data set with us to see what I'm talking about. All right, so like I was saying, this is an SPSS sample data set for 180, let's say, participants, or our sample size is 180, which you can see there. And like I said, those are my variables. I have age in here. The blood lipid level, presence or absence of stroke, I have hypertension, I have educational level, I have income, and then I have BMI again. I'm going to be using for a paired sample t-test with an assumption that maybe after some exercise, this is going to be the baseline BMI, this is going to be the BMI after exercise, that is the outcome BMI, just to see how we do those analysis. So, sorry, I will still have to just quickly go back and share some questions with us, which I think I will have to write down to reduce the amount of to and fro. Okay, so I have 1 minute. Just permit me to jot down these questions, otherwise our going to and fro will be too much. But I don't know if anyway, it wouldn't really affect much. So this is the first question using the sample data set I have. I want to check the relationship between age and BMI. So even forgetting the fact that these were there, this is the only thing I have access to. So I'm going to look at the two variables that are there. I have age and BMI. Age is a continuous variable. BMI is a continuous variable. And I'm trying to check relationship. So I'm going to be doing a Pearson correlation. And for a Pearson correlation, we start with a scatter plot, which I'm going to do scatter plot. And then we'll now do the correlation proper. That's the analysis itself. So let me just quickly go back to my data set. And then we do a scatter plot. All right. So I have here my data. I go to graphs. I go to legacy dialog. I'm coming. Let me move. Graphs, legacy dialog. And if you look at this legacy dialog, you will notice that we have a scatter plot somewhere there. I click on scatter plot. It brings me another dialog box. I just want to do a simple scatter plot. I select and then I define. And from the definition here, I said it is age and BMI, if I remember very well. So I go to age, I select age, I take it to any of the axes. It can either be on X or Y axis because it's a scatter plot. And then I go to my BMI, I take it to my X axis. And then I just run my scatter plot. Okay. And I'm going to stop sharing so that I can share with us the output of that analysis. I don't know if you can see that. Can we see the scatter plot, please?
Yes, sir.
Beautiful. So that's a scatter plot showing the relationship between age and BMI. And you could choose to, what's it called? You could choose to format it like I always like doing. I don't like the gray background here. So if I double click, I can remove that gray background and make it whiter for visibility. Oh, yeah, now. Okay, so I could just pick that, apply, and I can even change these small circles. I can give them the color of my choice, maybe like something like red, apply. And so we have that. That's a scatter plot. And for this scatter plot, I can put the linear equation, that's the linear line, the line of a straight line inside it. That one can be done by double clicking also. And then I pick the line here, that is the line of best fit. I insert it and I close. And you can see from there, we have our line of best fit there. So y equals to 30.3 plus 0.6x. And that over here is our coefficient of determination. So that, in a nutshell, is our scatter plot. Remember, we are looking at age and BMI. So let's go to analyze. In analyze, I'll go to correlate. And in correlate, I'm correlating two variables. That's why it's bivariate. And then I click on bivariate. Please, are you seeing what I'm doing, please?
Yes, sir.
Yes, sir.
Yes, we can.
Yeah, so I just go to, what's it called, age, like before. I move it to my variables. I go to BMI like before. I move it to my variables, And if you look at down here, there are options of the kind of correlation you can do. We have the Pearson correlation, and this one is chosen by default, and I'm sticking with that because my variables are quantitative and continuous. If both of them are ordinal, you have to come and tick a Spearman, but because they are, what's it called, continuous, I'm sticking with Pearson. And then there's a test of significance here, which is based on whatever type of hypothesis you have, two-tailed or one-tailed. I assume you have an understanding of what that is. And then if there are options of what you want to do, you can pick options there. But I would just say, okay, so that we can see so that's our correlation here. Our correlation between age and BMI. You can see here, this is our correlation coefficient, 0.269. And it's very significant. Our p-value is 0.000. It obviously has a figure, but it's very significant. And that will answer your research question, that there's a significant relationship, between BMI and age. And then you discuss that and you are done with that. So that is correlation in a short example. Let me go back to the next. Slide to see our next research question. I think it's going to be the next research question. I think is a chi-square. So let me just go to the next slide. Yeah, it's a chi-square. And for the chi-square, there are two examples there which I want to just write down before, so that I don't keep going and coming back. Sorry, I'm trying to get a pen to save us time without just going and coming every now and then. So the first one is education and hypertension. Education and hypertension. And the second one is stroke and hypertension. And we are going to do, what's it called? We are going to do chi-square for the two of them. So let me stop sharing here and then bring back our SPSS. Great. So I go to analyze. I'm not going back to the data set again because I realize that I have to close this window to go to the data set, close it. So I'm just trying to go through the output page to save us time. So I go to analyze. What am I trying to do? I'm trying to do chi-square. I go to descriptive statistics. If you look at descriptive statistics, there's one place where we have cross tabs, which I'm going to pick. And if you look at the cross tab, like I said, I'm doing, what's it called? I'm doing chi-square. And the first one is educational level. Educational level is here. I bring it to my rows. The second one is hypertension. Hypertension is here. I bring it to my column. Now, I said chi-square. Let me go to exact here and look at the function where I can get my chi-square statistics, sorry. You can see chi-square here. I tick it. I tick my chi-square and then I continue. In the cells, you have option. I can put percentages, by row, percentages by column, percentages by total. That one can be done if you so desire. But just to make it faster, I will just ignore that. And then I go, let it display the bar chart of that analysis, the comparison of those variables. Let me have a bar chart. And then I click OK. I click OK, and you can see here, it has shown me the cross tabulations here for educational level and hypertension. So those who did not have any education and did not have hypertension are about 28. Those with primary education without hypertension are about 31, and on like that. The same for this side where we have hypertension. And if you come to the chi-square analysis itself, the first thing you have to check is the p-value. And you can see it here, it is 0.955. That is not significant because our significance is taken at less than 0.05. So there is no relationship invariably between educational level and hypertension in the studied population. Now, going down, you will see an example of the bar chart, which we saw the last time we had our class for none. Those who don't have hypertension are blue. Those who have hypertension are green. So you can see here that in all, there are more people without hypertension compared with those with hypertension. That is just for that. I will quickly go back, and do the same analysis. This time around, I'll be using stroke instead of educational level. So what I will do here, I will just click the educational level, return it back to the data set, and then I will use stroke. So this time around, I'm comparing stroke and hypertension, and I want to see if there's any relationship. I click OK. And here you can see here, we have the 2x2 table here. Those without stroke, without hypertension, 92. Those without stroke that had hypertension, 23, and on like that for that table. And if you look at this particular analysis, you can see our Pearson chi-square. The p-value is 0.00, very significant. That shows that there is actually a relationship between hypertension and stroke. That's how we interpret that. There's a relationship between hypertension and stroke. And if you look at our bar chart, that is what we have there. This is those who don't have hypertension, and this is those who have had a stroke. Sorry, those who don't have hypertension, those who have hypertension, no stroke here, had stroke here. So you can see relationship. It's like stroke and hypertension are like twins. They are very close. The tendency of having hypertension is very close to having stroke. That is for, what's it called? That is for chi-square. Let me look at our next sample question.
Just to encourage us, apologies, we're just hold on here. We're exceeding our time, but please hold on. I think this is a very important class. Thank you, everyone.
I'll soon be done. I apologize for that. I'll soon be done. Okay, so we go to the next class, sample example. What is happening? Chi-square. Okay, the next one is t-test. There's one sample t-test, there's paired sample t-test, there's independent sample t-test. And I'm just quickly going to run through them, and have a sample analysis done for that. So look at this one sample t-test. Our variable is continuous. T-test is a parametric analysis. The outcome variable is quantitative. Now, for the one sample t-test, look at the sample research question. Let's assume that in one particular group of 180 participants, like I have done, is there an improvement in the lipids after a vegetarian diet over 3 days? And then we are taking our cutoff as 200. That is for our sample, one sample t-test. I want to just jot down the question so that I don't have to come back to this page again. And then for the paired sample t-test, it's like maybe one group now. And I'm asking that what is the difference in the average BMI before and after this group? So for this particular example now, I'm going to have 2 BMI reading. That is BMI before and BMI after. And I want to see if there's a difference in the BMI before and after in one group. That is why it is paired. So every participant has before and after. That's participant 1, participant 2 also has before and after, down to participant 180. They all have before and after values. So I'm checking their before and I'm checking their after value. So I'm going to write that one down, BMI, before and after, and that's for the second analysis. And then in the independent group, I just want to check if there's a difference in the BMI after this lecture. That is the outcome BMI, that's BMI 2, among the gender. I'm checking between male and female. Please note the difference here. The difference in this one is in one single group. But in this other group is 2 different groups. 2 different groups. So I'll just quickly go to the what's it called? This data set and run
Okay.
Vanessa, mute yourself, please.
All right, so I have what's it called? I have my data set here, and I'm going to run what's it called? A one sample t-test. So I go to analyze, and under analyze, what we do in t-test is we are comparing mean. And as you can see here, we have a one sample t-test, we have the independent sample t-test, we have the pair sample t-test, we even have the ANOVA here. But the one I'm doing is the one sample t-test, and I pick that. And you can see it's asking for my test variable. What I'm checking is the BMI, among a group. And I want to see if there's an improvement after them eating vegetarian diet for 3 days. And I told us at the beginning that my test value is 200. Let's assume that that's the value that is good below that value. Okay, let me see options. It is at 95%, so we are good to go. And then I click continue here, I click OK here. So you can see what we have here. This is our one sample t-test. You look at the p-value, it is very significant.
We're not seeing it. We're not seeing it. We're still seeing your. Yeah.
Oh,
we're not seeing the results.
Yeah, I had forgotten. Let me quickly do that. Sorry. Yes,
thank you. We can see it now.
Yeah, beautiful. So this is the one sample t-test, the statistics, the number of participants, the mean of all the values of the lipid, blood lipid level, standard deviation, standard error of the mean. And that is the one sample t-test using my test value of 200. These are all some values that we can discuss, if we are having like a t-test class, or yes. I can't go through all this because of our time, but I just want to bring out the fact that it is a significant finding by value of the p value here, and it's a two-tailed hypothesis test. So there's actually a difference in the lipid level, among that same group after doing a vegetarian diet for 3 days. So I go back, to the same compare means. This time around, I want to do a paired sample t-test, like I said before and after. So I have my paired variables appear over here, and then for the first pair, I have the BMI, that's the baseline BMI, I have it there. For the second variable, it is the same BMI after the class experience or whatever intervention we have done, I have it there. So I have variable 1, variable 2. Remember, it is a pair, it's in the same group. And then let me look at my options, it's also at 95%. Then I just continue, okay. And you can see it here, this is pair 1, and I have a summary of the, what's it called? Of the values, their mean, and the standard deviation and standard error. And here is the final pair sample t-test, and I go over to check my p-value, and I have 0.020, which also shows that it is significant, and then I can report my finding that there's a significant difference, in between the first and the second measurement. That means whatever intervention I did was effective. That is for that. Now, still going back to the analyze and comparing means, let's do the independent sample t-test this time around. And here now, it's going to tell me, what is my test variable. And I remember I said after the class. So I go to the BMI that was taken after the class. That's my test variable. And then what is the variable I'm trying to group them with? And I said gender. So I come to gender here. I bring it to my grouping variable. But it's telling me to define groups. And I come here and I'll explain what this one means. This means that when I was doing my data collection, how did I code male? And it was coded as 1. That's what I'm defining here. How did I code female? It was coded as 2. That's what I'm defining here. And I said continue. And once I have put my test variable here, and I have my grouping variable, I have defined my groups, the next thing is just okay. And then we have our independent sample t-test here. Like I said earlier on, I wouldn't go through all the way on how to interpret these tables. It's one of the classes that I normally take, what we have here is the Levin's test of homogeneity of variances. But whatever that is for now, we are not looking at that. But we are checking our p-value. And as you can see, the p-values are far way ahead, greater than 0.05. So it is not significant. That means that there is no change or relationship. There is no difference, rather, between the BMI among the male and the BMI among the female. It's as simple as that. That is just, 3 samples of t-test, the independent sample t-test, the dependent sample t-test, and the 1 sample t-test. This is the last set of analysis, and that is for the regression. I will just write down the questions and quickly we run through that and we are done. So let's go to the next slide. Oh, there's what's it called? There's ANOVA. Okay, let me just write ANOVA down. We will do everything. ANOVA has to do with baseline. That's baseline BMI and education. Remember I said ANOVA has to do with anything that has more than 3 categories. And in my data set, it's only education that has more than 3 categories. It has 4. Okay, let me just go to the next slide. So linear regression, I want to write it down so that I don't have to come back here. I'm checking between age and lipid. Multiple regression, I'm checking multiple regression. I'm checking age, income, educational level, and lipids. And then logistic regression, which is the last slide, logistic regression. I'm checking income and hypertension. All right, so let me go back to my output slide so that we can run this analysis. So the first one I will quickly do is the ANOVA. So I go back to my analyze. Remember, it's compare means, and then we go down to one-way ANOVA. There's actually 2-way ANOVA. There are 3-way ANOVA. There are many, but this is what we are just going to look at for now. And for our ANOVA, we are checking the dependent variable. You can see it here. And our dependent variable is the BMI. We are checking the BMI. And our factor here is the educational level. We want to see how it affects, the BMI. Let me see. Okay, let me just Let me just OK it so that we continue. And as you can see here, that's our ANOVA. Our p-value here says 0.7. That shows that it is not significant. That means that educational level does not have any impact, on, what is it called, on our BMI. That is all about ANOVA. So there's one thing to analyze, there's another thing to interpret, but we are just looking at how to analyze. So let's quickly go to regression and look at how to analyze that. We have age and lipid level. So I go to analyze, I come to regression, and I come to linear because it's just simple linear. I pick linear regression, and it's asking me to pick my dependent variable. So you can see why we need to know dependent and independent. And our dependent variable is the lipid level. So I pick my lipid level, I put it to dependent variable. It's asking me for independent variable. So for here, I'm using age, and I put it here. So if I have only one independent variable, that makes it simple linear. But if I add extra independent variable like I will do after now, that makes it multiple linear. So let's just look at this and continue. And then we have our, so when you are doing regression, it actually comes with a sample ANOVA table as part of the analysis. But let's just come to our analysis. So we have here our simple linear regression between age and lipid level. And what we have here is significant, 0.008. That shows that age actually has an effect on the lipid level. Remember, all this data is just hypothetical. That's simple linear. So I go back to the same analyze, I go to regression, I go to this time around the same simple linear, but the only difference here is that I'm going to add more variables here to make it multiple linear. So here now, I'm going to add income, that's per day in Naira, as part of my independent variable. I can add educational level. I can even add more. Let me even add the baseline BMI. I'm just adding variables just for the sake of it. So we have about 4 independent variables. And then I go back, I do my analysis, and then I have here my findings. So from my findings here, for my age, at this level, it's no longer significant, a predictor for lipid level. My income is not significant. My educational level is not significant. Only the baseline BMI is significant because it's the only one less than 0.05. You will notice that there is 0.000 here. This one is a constant. It's not a variable. It's not an independent variable. Likewise, on the former one too, let me show us. You can see it's also here. It's a constant. It's not a variable. So we are not looking at that. We are only looking at those that are our independent variable. That's this last 4 here. And lastly, I'm going to do, what's it called? A logistic regression. So I'm still going back to regression. And then here I come to binary logistic. Remember I said in logistic regression, our Y is binary. And for our Y here, I'm looking at presence or absence of hypertension as my dependent variable. And I'm trying to look at their income as my independent variable. Now, because I'm putting only one variable here, it's just simple binary. If I have more variables here, it becomes multiple logistic. Just the same way with the simple linear and multiple linear. So let's just check what we have here. And then we have our outcome here. Variables in the equation is just income, only one variable. And our income here is 0.997, no, sorry, 0.158, which shows that it is not significant. This exponential B is the odds ratio, in logistic regression. And this is like 1. And when we have an odds ratio of 1, it just means that there's no difference. It doesn't have any effect because 1 means that it's 100%. It doesn't have any effect on the dependent variable. I believe that is the end of the slides. I want to thank you for your patience, and I will be able to entertain some questions briefly before we go if there are. Thank you for your time. Yes, that's the last slide.
Thank you very much, sir. As usual, it's a very enlightening session for all of us, both the fellows and we also attending. Thanks a lot. Probably been asking some important questions on the page, but I think the fellows should come up first, then I'll go to the questions on this chat box. So any fellow, okay, one hand. Any other person, please, I need all the hands up. Okay, I think it's only Okeke that has a question. So Okeke, please go ahead.
Okay, thank you very much, Dr. Taiwo. This has been a very wonderful class. A lot of value given in just about an hour. I even wish you could even stay more. So I had a lot of questions, but while the class was going on, some were answered.
Okay.
So I will need the clarification in others. First of all, I think the most important for me right now is I would like you to throw more light on the odd ratio.
Okay.
One is because I thought that, or I know that they use the logarithmic regression to predict maybe future occurrence of probably an event.
Yes.
So yeah, but I don't really know that much. I would like you to throw more light on it. That's the first question. Secondly is, does the SPSS app have a section for multiple linear regression, or do you need to keep adding more variable to the simple you've done already? Is there no section for just the multiple linear?
Okay.
Then also, how did you insert the linear plot? That is in your scattered plot. How do you insert the linear?
Okay.
Yeah, because I didn't really get how you did that. You just did it very fast.
Oh, I'm sorry. I was trying to catch up with time. Okay.
Okay.
So
Also, okay.
Continue.
Should I complete the question? Okay. Then what's the difference between the ANOSIM and the ANOVA in terms of analysis itself? What does the ANOVA intend to achieve? And what does the ANOSIM intend to achieve? Is there a difference in terms of their approach, or is it just by definition?
Definitely, there's a difference. So let me start with the odds ratio. The odds ratio is just like a kind of prediction, the odds of something happening, not the probability, the odds of something happening. And the odds ratio is actually the odds of an event happening over the odds of an event not happening. I want you to get that. That's the ratio. So there's an odds of something happening and an odds of something not happening. So when you say logistic regression is used to predict, that's true. And the prediction effect size for a logistic regression is the odds ratio. So when you have an odds of something that is the ratio of something like 1, when a ratio is 1, based on the definition of odds ratio, that means the numerator over the denominator is equal. That means there's no difference. That's why the odds ratio, when I say 0.997, there's no difference, is because it is nearly 1. So that means it doesn't have any effect on that. There's a way you interpret odds ratio, and it's based on the values that you have. So logistic regression is used for predicting regressions generally. So when you have a research question like what is the effect of A on B, you are talking regression. You understand? Or logistic regression or multiple linear, whichever it might be. But I can't go so deep on odds ratio because it's actually a class on its own. It's actually a class on its own, but that's just on the summary that you use it to predict, and the values differ, and the different values are what you use in explaining your finding. So for the SPSS, the multiple linear is the same thing as the simple linear. It's just the addition of more independent variables that make it multiple linear. I have not come across a special, drawdown box that is multiple linear. But like I explained, once you have a simple linear and you add more variables, automatically it is multiple linear, but not as if it has any special. I'm not an expert with SPSS. All this I've been showing you are just my own little kindergarten level understanding of SPSS, which suffices for me anyway. I'm not a core statistician, but I just enjoy working with it. Now, for that line, when you double click on your output, especially your scatter plot, you will see a table that will end. Yeah. Is it a table? No, it's not a table. It's a row of some options that will come up on top of the chart. You will see one of them has that line. It says line of best fit. Once you click that line of best fit and apply, that is all. I don't know if I can go through that again because of our time, but that is how that works. It's just you see that row of options, and you will see a sample line on one of those rows of options. Once you click it and then you apply, it will bring in your line right there in your chart and brings you your coefficient of determination. That's the R squared. For the ANOSIM, analysis of similarity, ANOVA, analysis of variance. Definitely there are two different analyses. I have not used analysis of similarities before. I have worked with ANOVA severally, but there are two different analyses. One of them is checking differences, one of them is checking similarities. So it will be dependent on the kind of research question you have that will make you choose the particular type to work with. I hope that makes a bit of sense.
Yes, sir. Thank you very much, sir.
Thank you very much, sir. I'll take some of the questions on the chat box. The first one I'm seeing right there is in the ANOVA analysis, there is within group and between group.
Yes.
So what's the difference and what do they imply? Then also to take it together, the constant in the regression analysis, what does this stand for? And what's it important?
Good questions. I don't know where to start from. Now, for the within group and the between group, maybe in future, Dr. Lawal, I think it's better because it will be like just plucking the leaf off the tree. There are some background that had to be placed before I can explain these things. When you are doing ANOVA, there's actually a class on ANOVA, the basic ANOVA, and likewise the one we are talking about, the constant. The constant is the equation in a straight line, y equals to a plus bx. Let me see if I can do something. Y equals to a plus bx. That a plus bx, that a in that equation is the constant. I'm coming, please. Let me see if I can just annotate something here. So the equation of a straight line is this: y equals to a plus bx. This is for a simple linear regression. Y equals to a plus bx1 plus plus cx2 plus dx3. This one is for a multiple linear regression, where this one is the first independent variable, the second independent variable, the third independent variable. When you draw a straight line like that, like the one Dr. Okiki was asking, the place where that line hits the y-axis, that is the constant when x is 0. When x is 0, that means this one is 0. That means the place where y equals to a. So the position where this straight line hits the y-axis, that is what we call the constant. It's one of the factors in a simple linear regression equation. And likewise, you have it when you even have a multiple linear regression. So A is the constant. Sometimes you will see, they will say y equals to a plus bc. This c is the independent variable. Sometimes they say y equals to beta naught plus beta 1x. This beta naught is the constant. It depends on how the equation is written, but that is the constant. For the ANOVA you were talking of between and within, that one, I don't know how I can just explain it in a nutshell. There are
It's
some
okay. We can take another class, another
Yes,
independent class.
It will
We will
be easier
arrange
that
it.
way.
Yes, sir. Yes, sir. Yes, sir.
Thank you, ma'am.
Thank you so much. I think it's been a brilliant class. We just have about 4 more minutes to end. I don't know if there's any other class student that wants to answer this. I'd actually noted that a statistical class should be made 1.5 hours. And if we do respect that, we're just still in time. If there's any other person that has a question, otherwise, we will be bringing the class to a close now. We want to thank Professor Taiwo. I mean, your statistics class is always brilliant. I'm probably going to arrange a class with you to address a few queries of mine. But let's show our appreciation for the last 2 classes. This is our last statistics class. And just to also inform Professor Taiwo, the entire fellowship will be ending in another 2 weeks. Yeah, maybe 3 weeks. And we look forward to you being there with us. Thank you so much. It's been
Thank
really
you so
brilliant.
much, ma. Thank you
I
for
wish
having me.
I'm definitely going to have another session and bring you
No
on
problem, ma.
to continue this.
Yes,
All
ma.
right, everyone. I hand over to Dr. Kudus now as we end this session. Over. Thank you.
Yes, thank you very much. Thank you very much, Prof. Tayo, for this beautiful session. As usual, we always learn whenever you come around, and we appreciate you for your time. So that
Thank
marks
you.
the end of the statistics class for this cohort of monthly writing fellowship hub, and we'll meet next week to continue the session on the manuscript writing. Thanks, everyone. Man, you can stop the recording.